Everybody, good morning. Today's subject is energy, the deformation, especially we're going to talk about the deformation energy. Actually, if you open the textbooks regarding mechanics of materials or structural engineering, always there is at least one chapter where the authors are talking about the energy issues. But none of them doesn't provide, the general overview of the energy issue. That's why here I'd like to provide you some general point of view regarding the energy issues. So I hope you can get clear concept for the energy issues, deformation energy. So let me talk about my story. Talking about total energy in a system. So let's consider a system. Then if the system means it can be a structural system, or it can be, you may consider like, how to say, a set of particles, or you can consider a pot where you put 라면 끓이는 그 주전자. So whatever, you can consider any kind of system. The total energy in the system can be represented by the sum of all the energies in different forms. And this is very important, in different forms, okay? Which means the change of energy in the system is the sum of change of individual energies. For example, here K, typically they represent, using K they represent the kinetic energy, and then U, they use U to represent deformation energy, and H is for heat energy. And what else? For example, so if you consider like Jean Grey in X-Men, she has a psychic power. I don't know if there exists any psychic power or whatever. Okay, well, so unless you consider any nuclear power here, the exchange of mass and energy, and then this rule should be preserved. Okay, this rule should be there should be if you consider any system, there should be interchange of energy in different forms. So and the shape of energy changes from the one type to the other type. Okay, and then especially as I told you, the energy may have different forms: the kinetic energy and deformation energy, and the potential energy and the heat energies. The energy generated by a force vector here, F, in the direction of displacement, U, is called work. Okay, so work is a different a form of energy. So you may consider work is a subset of energy in a system. Okay, it's not different from something else. Okay, it is a form of energy. So here, by this definition of work here, the change of work dW, typically the work is represented by W, or here the work W, it starts with W, that's why we like to use W. So dW is equal to the work done by force F, the vector, and then in the direction of displacement, because of this we put dot product. Okay, dot product. So which means, for example, okay, let's consider a force here, force F, and then let's consider the direction of displacement here. Okay, it's normal. Then in that case, the dot product between the force and displacement is what? Is equal to 0. Okay, so in this direction, this force doesn't generate any work. This is the definition of the work generated by force F in the direction of displacement. Do you have any question here? This is very simple, isn't it, right? So if you consider a system, so you can measure the total energy change by checking the changes of individual energy forms, the change of kinetic energy, change of deformation energy, change of heat energy, and then what else? And change of work, and the change of psychic energy. Okay. And then especially if you want to measure the total work, then we need to integrate the work, isn't it, right? The total work is, we need to integrate the small work, okay, small work. But here, if the force depends on the displacement, then we have to write the information of work in this way: the integration of force dot and du. And here the force is a function of displacement. Okay, what kind of example that we can see such kind of behavior? The force depends on the displacement. So for example, for instance, let's consider offshore structures, the offshore vessel. For example, let's consider cross section of the ship vessel here. And then the pressure on the bottom of the structure depends on the draft, isn't it? See here. So the pressure is equal to the specific weight of water times h, isn't it? So let's consider my ship is subjected to some kind of displacement. For example, we have some displacement like this, such that this is equal to h plus u, for example. Then the pressure becomes what? The pressure becomes gamma w h plus u, isn't it? Certainly here the force depends on the displacement. This is a good example where the force depends on the displacement. By the way, excuse me for a while. So I have a visitor here.
다름이 아니라 그 이종용 교수님께서 갑자기 부르셔가지고 이거 관련해가지고 그냥 종합시험 관련해가지고 한번 찾아보면 될까요? 이 양식 들.
Okay. Sorry about it. And then let's consider an example. Here we want to consider an example in which the force doesn't depend on the displacement. One of the good example in these kinds is the gravity, isn't it? For example, let's imagine that I stand on top of a platform here. Then I'm subjected to my body weight, the mass times the gravity acceleration. The directional force is downward. So make sure that wherever I stand on, then my gravity load is still the same, no different. So let's try to calculate the work done by my movement, okay? Initially, I was standing on the position characterized by x0 vector. And then I move my position to x1 vector, okay? So I can walk through following in this direction, or I can jump over to this direction, so whatever, okay? Or I can just step down here and then I move to this direction, whatever. So what we want to do is I need to integrate the contribution of the force F in the direction of displacement in the path from x0 to x1. Okay, that's what we want to calculate it. So here, since my force vector, the force vector is characterized by mass and the gravity acceleration. Here, gravity acceleration is another vector. That's why we can take out because this force has nothing to do with the displacement vector. So I take out the force vector and dot product to the front of this integration. And the calculation of this integration is very easy, isn't it, right? This is F dot and x1 minus x naught. And that becomes nothing but just F dot and then the change of the position vector. So this is nothing but, if you calculate this, because it considers only the dot product in the force direction, so it becomes just mass times gravity acceleration times the height of platform, mgh. This is a well-known formula when we want to calculate the potential energy of a mass, isn't it? So you pretty much familiar with this. Do you have any question here? Are you clear? Okay, so if you don't have questions, so let's move to the next page. So now here, let's consider a little bit more advanced topics. Here, we want to consider the energy conservation issues. And then also, I want to consider two different examples, the first one and the second one. In the case of first one, we have a mass initially here, and then the mass is subjected to the mass times the gravity, or I mean the gravity load, and then initially the mass was the velocity of mass was equal to 0, and then it may be accelerated, isn't it, by this movement. In the second case, so we want to consider exactly the same situation. We have mass here, so mass here, and then the mass here, the mass is moved by dx, but now in this case, this mass is attached to any fixed support by means of a bar here. Okay, so we have two different situations. So this first one is a free falling problem. The second one is falling body, but the body is connected to a bar and then to a support through a bar. Okay, so now let's consider the change of potential energy. So the change of potential energy is given by this. Actually, if the mass drops, then it's gonna lose its potential, isn't it? So that's why this is the gravity force dot dx. So because it's losing its potential, that's why we put the minus sign. This is a change of potential energy. And then let's consider energy balance. In overall system, there is no energy change. For example, let's move back here. The total energy change should be equal to 0, unless we consider any nuclear reactor power. So energy, according to the energy balance, the change of potential energy plus change of kinetic energy should be equal to 0. So then we can calculate the kinetic energy very easily, isn't it, right? Here, this is given by mg times mg dot dx. Then we can calculate the kinetic energy very easily. In the second case, what? We have to consider, because that's subjected to some mass times acceleration. And then in the second system, we need to consider is kinetic energy. And then, by the way, here we don't want to consider any mass of this bar. So we don't want to consider any the mass for this bar. And then the change of potential energy. The change of potential energy is exactly the same in these two different systems, because we want to consider just hypothetical problems. And then here we have a body here, okay, deformable body. And the deformable body would have some change of deformation energy, isn't it? So this is work balance now. So this is the system 1, system A, and this is for system B. Okay? Any questions? Alright, so let's move to the next slide now. Now we want to calculate the change of the kinetic energy now. the change of kinetic energy. Kinetic energy there is a well-known formula, isn't it, right? The kinetic energy is a half times mass times v square in scalar form. But in vector form, we have to write in this way, v dot v, isn't it, right? This is vector form. And then let's take the derivative. Then if you take the derivative, we have what? I have factor or half. Let's move out or half, or half, and then I need to take derivative for v and another v. That's why we need to we can have, because we have two different terms and then factor or half. That's why we have mass times dv dt. Okay, and then here well, let's do one by one. Let me show you this derivation. Okay, let me show you the derivation. So here the half m mass and velocity dot velocity is equal to, so here I have a half of mass and then d v dot, isn't it? And this is equal to a half times mass and then dv dot v plus v dot dv. So we have exactly same quantities. That's why we can cancel v or half here. This is equal to mass times dv times v. Okay. And then here the v depends on time. V changes by the time. That's why instead of dv, then we can write dv and dt times v dt. This is what happened. Okay. Here the mass times dv dt is acceleration. And then v dt is what? The v dt is equal to dx. Any question? This is the kinetic energy of system B. Now let's talk about work done by the external force. Here the external force is what? The mass times the gravity, okay? And it doesn't work over the displacement. The mass times gravity dot dx. And then the third term is work done by the stress during deformation. So we'll discuss it later. So I want to talk about this is du. This is the internal work done by the stress. So now let's talk about the work balance. So if you talk about work balance, then the difference between the external work and the internal work should be balanced by the kinetic work. Okay, here the kinetic work is given here. And in the case of static system, so kinetic work is equal to 0. That's why in the case of static system, we have change of external work is equal to change of internal work. This is the work balance equation. So now here I just let the internal work is equal to du, but I didn't define, or I didn't calculate du. So here let's try to calculate du here. Okay, so we are talking about mass and then attach it to a boundary by using a bar here. Okay. And then if you isolate this bar, let's isolate this bar, then we have this. Okay. And then we have some kind of stress distribution. And then if you consider this stress distribution, So on the bottom surface and the top surface, we must have traction, isn't it? And then even if you cut here, if you consider imaginary surface, and then again we have new surface. Here we have a stress field, and then also satisfying force equilibrium, you must have another stress field. Actually, this traction doesn't work, in the displacement in this direction, and also this traction doesn't work in the direction of that displacement, isn't it? Okay, and then these guys too. This is traction, surface force, what I mean. Traction doesn't work in this direction, isn't it, right? This guy also do work in this direction. So here, let's consider one by one. So if you want to calculate the internal work, let's try to calculate the internal work. For example, I want to consider this guy here. For example, let's consider this guy. The calculation of internal work is what? The work is the force dot U, isn't it, right? The force dot product and U. So this is traction. To change the traction to a force, we need to multiply the cross-section area. On the T means on top surface, okay? On top surface here. The top surface traction times the area is the force. And then we now consider dot product in this direction. That's what we want to do. This is the work done by the traction on top surface. And then here we have another traction here. Traction on the bottom surface times the area, and then displacement U, dot product. So here, look at this. And then here, look at this. Because the system is in equilibrium, traction on the bottom surface is equal to minus of traction on top surface. So let's plug in here. Then instead of TB, it becomes minus TT. And then UT. Okay, so TTA dot DUT plus TB, traction B, and times the area, and then du dot B. Okay, so as I told you, traction on the bottom surface is equal to minus of traction on top surface. Then here, this is equal to traction on top and area dut minus traction on top surface A dub. And this is equal to traction top dot dut minus dub. So please note that this is equal to change of displacement d delta u. Okay, that's why we have this equation. Okay, let me copy the equation here. So here, the traction on top surface times area is equal to what? This is nothing but just normal stress, isn't it, right? The normal stress. And then d delta u is equal to what? This is the strain times the original length, isn't it, right? By the definition. So finally, we can obtain stress times the internal work can be given by the stress times the change of strain, and that is volume. Okay, it's volume. So here we consider two different segments, the first segment and the second segment. So the internal work of whole system is sum of internal work calculated for the first segment and the second segment. So here, instead of talking about only two segments, we can consider infinitely many segments. For example, here, very, very small segment. Then we can generalize the calculation into integration form. So internal work is defined as integration of normal stress times the change of strain and over the volume. And then here, stress d sigma d epsilon is defined as d u bar. Here u bar is defined as strain energy density, because this is the strain energy per unit volume. Do you have any questions? Okay, so here I'd like to summarize our discussion here using my diagram here. So if I summarize the overall configuration here, so in this diagram, so we have external force and a displacement. So make sure that these two form work conjugate, so energy conjugate. It doesn't work. This is a structural scale. It produces external energy, the external work. In the case of static system, this external work should be balanced by the internal work. The internal work is work done by the stress at material point level. So we need to integrate over the volume. Okay, integrate over the volume. And then here, this is called internal work. Clear? Okay, here I'd like to take a 10 minutes break.